thanks, Daniel, for the introduction. And I've had a great time. Well, so far at the workshop, and I hope that the next week will be this. So talk's gonna have 3 parts. In the first part, I'll just introduce flow problems. This is the Maxflow and the electric flow problems. In part 2, I'll talk about data structures for electric flows. And then in part 3, I'll give a heuristic analysis of why our electric flow data structures imply an improvement in Sparse. So just to give a refresher for the maximum flow problem, I might recruit because we talked about this a couple of times. But maximum problem with a directed graph, and every edge has, let's say, an integer capacity from 1 to capital U. For the purposes of this talk, it's actually useful to think of as larger, so like larger, so polynomial now. Let's say like m cubed or something. So we're not dealing with unit capacity max flow. Audio is very low. It's so.
Now you should be heard.
Okay. Well, hopefully the audio is better now. Okay. So yeah, just to keep going. Yeah. So the goal is to route a flow as much from S to T as possible. Okay. So that you're within the capacities on every edge. For example, given those capacities, here's a flow. As you can see, for every vertex, the amount of inflow is the same as the amount of flow going out, and the total number of units routing from S to T is 4. So yeah. And in general, for the purposes of this talk, we're going to let F in the space R to the E be the flow vector. So FE is the amount of flow on edge E, let's say in the direction given by the edge. Okay. So so there's a bunch of other variations that are useful to keep in mind. Maybe a more optimization way to think about this is we're just going to ask, can we route F units? So it's some decision version. We're going to use this primarily. And we're only talking about ST flows because general demands can actually be reduced to ST by adding a super source and a super sink. So yeah, we're going to focus on ST max flow. This has some interesting things I'll discuss later. And we'll let the demand vector D sub V be a vector, which is just kind of what the flow we want to route. And if the demand is routable, then you need the sum of demands to be 0. And finally, we're just talking about directed max flow, but exact directed max flow is equivalent to exact undirected max flow. So we'll focus on the undirected version. As for why maximum flow, we talk about it at all. In general, it's a very fundamental problem, but maybe for people here, it covers a ton of different things that are interesting. So bipartite matching, scheduling, clustering. Additionally, if you generalize max flow a little bit to maybe like a more linear program setting with a linear constraint, you start covering min cost flow, negative way shortest path, min cost matching, or optimal transport. There's been a ton of work on maximum flow in the past. So just a lot of stuff in this chart. I'm going to focus on a couple of results in here specifically. In the first result I want to talk about is this Goldberg-Rao result, where they get a runtime of m to the 1.5 with a polylogarithmic dependence on m and u, which is what we're going to focus on here. And I guess until this work, this was the state of the art. Or like until recently, this was the state of the art in basically all capacitated settings. And another thing I wanted to point to is actually a strongly polynomial algorithm for max flow. But the reason this is interesting is because this was an early use of dynamic data structures to actually make max flow faster. Like the blocking flow iterations were done using things like link cut trees or dynamic trees, and that's how they achieved their runtimes. So the previous slide was like path-based max flow algorithms. The algorithms were based on pushing paths in the flows, pushing paths to get the flows. More recently, everything has actually been done with electric flows, and that's kind of what's on this slide. This started from the work of Deitch and Spielman, which noted that you can solve a min-cost flow or other types of flows by using a Laplacian system solver to implement an interior point method. This way they got a matching m to the 1.5 time algorithm for Maxflow. And the way it works is I'll do an interior point method, which is square root m iterations as we've seen today. And every iteration is m time due to a Laplacian system solve. This result has been improved in several ways. One of them is the results of Lee-Sidford, which got a root m iteration IPM, and thus you get m root n time. And another is on unit capacity graphs, you can do some sort of acceleration and get an m to the 10^7 runtime. More recently, some work that Jan discussed is that you can actually start combining data structures with these interior point methods and get faster runtimes. This is m plus n to the 1.5. And what I'm going to be talking about in this talk is how you can actually, even in a sparse graph, get slightly faster than linear time per iteration in these methods, and thus like the first faster algorithm faster than Goldberg-Rao for Maxflow in sparse graphs, sparse capacitated graphs. Okay. So as discussed, all these algorithms use electric flows. So an electric flow on a graph, every edge has a resistance, Re, and the goal is to minimize the total energy over all flows that route one unit, let's say from S to T in the graph. And the total energy is denoted by the sum of Re Fe squared, and we'll let Re times Fe squared be the energy of the edge E. Just to gain some intuition for what it could look like, let's look at the following graph. In this graph, let's say every edge has resistance 1, and we want to compute an ST electric flow. What ends up happening is that the flow is going to put 1/2 unit on the single ST edge, and then 1/6 unit on each of the paths of length 3 between S and T. So somehow it's like an interpolation between it wants short paths, and it doesn't want to put way too much on any edge. So it's like, well, this makes sense because it's an L2 problem, and L2 is between L1 and an L infinity. L infinity is max flow, and L1 is shortest path. As for why electric flows have been studied, they're supernatural because they correspond to solving a linear system on the graph called a Laplacian. And they can be used to estimate hitting times of random walks, like do spectral graph clustering, etc. And in particular, the kind of random walk approach or effective resistances also have applications in traffic modeling. And we'll use the random walks interpretation later. They're a very powerful primitive on the other hand, and they can be solved in almost nearly linear time due to some seminal work of Spielman and Ten. In fact, this runtime's actually been improved. Like it used to be log to some large number. Now all the log factors have been removed. So now we're down to reducing log factors for this runtime. And it's been used in several recent advances on the Maxflow problem. At this point, I'm going to go into a little more detail, intuitively at least, about how to use dynamic electric flow data structures to solve Maxflow. It's a slightly different treatment than maybe what Jan had talked about in the first talk today. So in general, an interior point method shows that you can solve Maxflow by solving a sequence of square root m linear systems. Another way to look at it is I can build a maximum flow by using a sequence of square root m electric flows somehow. I guess, yeah, this is made more formal in Madry 2016, where he gives a way to look at building a Maxflow by just augmenting by a sequence of square root m electric flows and doing some pre-process, like doing some extra processing in between. I think this should be contrasted with the classical approach of using augmenting paths to solve Maxflow. Here we're using a sequence of root m augmenting electric flows. So yeah. The basic approach we're going to look at is how do we construct a Maxflow by augmenting by root m electric flows. If you just naively use root m electric flows, then you get a runtime of m to the 1.5 because every iteration is a linear runtime of m. And as for how to get past this barrier, there's two approaches that have been taken. In the first approach, you just want to reduce the number of iterations. We just don't want to do root m iterations. We're just going to do less. It seems that to this point, at least, it's only known how to do this for unit capacity graphs. And what you get out of this is up to now, you get m to the 1/3 iterations, and the total runtime is m to the 4/3, and it's only unit capacity. The second idea is closer to what was discussed earlier by Jan, which is what if we actually can just make every iteration faster than m time? What if you just don't pay m time every iteration? And yeah, that's the approach we take. So towards this, the first observation is that you don't need to solve the exact electric flow every iteration. You can use something much, much cruder. In particular, you just need to somehow form an estimate of the electric flow every iteration. And you only need to form this estimate on a graph where every resistance is off by a 1.1 factor. Like, you're also just okay with that. So the refined approach along these lines is, what if we just only update the edge resistances that we're trying to understand when they change by a 1.1 factor? And this only happens O of m total times. And additionally, on this graph where the resistances have changed very slowly over time, we want to dynamically maintain what are the new edges who change a lot and we must find. So maybe more precisely, we're given a graph G with some resistances and they change over time. And then after every change or every batch of changes, you just want to report, tell me which edges have a large ST electric flow. And then the algorithm is going to update these edges and keep going. So at a high level, if we're able to build a data structure that supports these sort of updates and queries, where every update and query runs in sublinear amortized time, so m to the 0.99, let's say, then we can get an algorithm that's faster than m to the 3/2 of Maxflow. There's a large sequence of reductions, but this is the high level idea to keep in mind. We just need a data structure that supports resistance updates and query what are large electric flow edges in sublinear time, and then we're good to go. So along these lines, this is our first result. We build such a data structure. So formally, here's the data structure. We give a randomized data structure against oblivious adversaries. And under the guarantee that for the input resistances, that the electric flow value is at most 1 at all times, we can initialize the graph, update the resistance of any edge, and finally return return a superset of edges S that contains all edges E with energy at least epsilon squared. And we call this the locate operation. And we give an algorithm that supports all these operations in m to the 0.99 over poly epsilon amortized time per query. And yeah.
And just to clarify, do you actually return the value of the electrical flow on the large edges, or do you just need to know where they are?
So yeah, the question was, in this data structure, do we just locate the large edges or return the value on them? We can find the subset of edges. This is the harder part. And then given these edges, we can estimate their flow values up to a 1 plus epsilon. Yeah. I also thought it might be good to stop for a couple questions right now before I went on. Yeah. Yeah. Okay, maybe let me just make a couple points then. I stated the data structure against oblivious adversaries, but in general, if you ever want to apply data structures to an algorithm, you actually need it to be against adaptive adversaries. I'll give a brief description of how you get around that issue later. And yeah, otherwise, this is kind of what I'm going to talk about for the second half of the talk. One thing I wanted to point out is that this data structure only actually works for ST electric flows. And I think it's a good question how to make it work for general demands. I think this is especially strange because, as I described earlier in the talk, ST Maxflow and general demand Maxflow are actually equivalent problems. However, this data structure uses some very, very specific properties of an ST electric flow to actually get the runtimes. So clearly means there's something fishy there that we don't understand well. And given this data structure, we're able to give an algorithm that solves capacitated Maxflow in runtime m to the 3/2 - 1 over 328 log u. And yeah, this is the first improvement to the m to the 1.5 runtime of Goldberg-Rao. And at a high level, the way we do it is we implement a sequence of root m electric flow augmentations, except very, very crudely by using this previous dynamic data structure. So yeah, for the remainder of the talk, here's kind of the parts I could talk about and what I'm actually going to talk about. The first part is the dynamic electric flow only works for ST electric flows. We're going to talk about this whole data structure and kind of where that comes from. And another part, the data structure only works as described for oblivious adversaries, but we need it for adaptive adversaries. I'll describe how to get that. And finally, the actual interior point method has to be changed to interact with the data structure. I'm not really going to talk about that, but at a high level, what's going on is, as I described, the data structure only works for ST electric flows. What you think about that is, when I actually implement the interior point method, I'm only ever allowed to solve a linear system on the actual demand vector I care about, which is not normal. Normally in an interior point method, you're solving a linear system on various vectors. But here we need to make sure it's only ever solved on a fixed vector always, which is ST. And in that way, we have to actually change the way the whole outer loop works to make it work. But we're able to prove that you can do this by losing a few extra factors in the convergence analysis. And combining all these things is where the kind of very tiny runtime improvement comes from. Okay, cool. So now, yeah, let me try to give an overview of how the data structure actually works or what the pieces that go into it. Maybe I won't get into the details at the end, but yeah. Actually, sorry, let me check real quick how I'm doing on the time so I can decide.
Yeah, your clock up there.
There's a clock up there. Okay, cool. Great.
You have
Okay.
between, let's say, 10 and 15 minutes, but it took about 5 minutes.
Yeah.
So
Okay, great. Okay. So, okay, I'll just do this part a little, maybe more briefly. Okay, so the goal is to build, the goal of the general dynamic data structure field in graph algorithms is to, build a data structure that hopefully in sublinear update time supports maintaining some property of a dynamic graph. So examples of this are flows, shortest paths, reachability, and the one we focus on is effective resistances. And the approach that's generally taken is some sort of graph decomposition. You want to reduce the problem on the large graph to some problem on a smaller graph. Another way to view this is vertex sparsification. So let's just say for the case of effective resistances, you would want to reduce the number of vertices of the graph while preserving effective resistances or flows or whatever between the vertices that we end up caring about. So towards this, for edge connectivity, it's been shown how to use vertex sparsifiers for edge connectivity to get faster data structures. And there's also improved bounds for approximate shortest paths and flows. And for the purposes of the remainder of this section, we need to focus on dynamic effective resistances. So this is sublinear time for 1 plus epsilon approximations to the effective resistance in a dynamic graph. Okay. The way to do this is, well, the way that it's been done is to look at Schur complements. So given a graph given a graph, we let B denote the edge, vertex, and matrix, and the Laplacian is B transpose R inverse B. The effective resistance of an edge E is given by the inner product of chi st, which is the demand vector denoting that edge, inner product of that with respect to the inverse Laplacian. So we want to maintain that. So in this vertex sparsification language, our goal is to compute or maintain a subset C that contains the vertices S and T, such that the inner product of chi st with respect to the Laplacian inverse is kind of maintained but localized to the set C. And this is called a Schur complement, and here's the example I'm going to give. So concretely, we want to build a matrix L sub C on a subset C of vertices that kind of maintains the inner product exactly. So let's say that we have this original graph, and you want to maintain the inverse Laplacian form onto this subset of 3 vertices. What you can do actually is you can kind of delete the vertex on the left and add this triangle to the right, and then compress these 2 parallel edges into a single edge. And that ends up being the Schur complement. So yeah, you can check that this graph actually has the same inverse form restricted to the 3 vertices as the graph on the left. And once we have or able to maintain this matrix L sub C, then you can kind of store the inner product or like maintain the inner product. So just to say a couple more words about this Schur complement matrix. If you let the Laplacian be LFF in LFC, LCF, LCC in block form, then the Schur complement is given by this formula. But maybe more intuitively, this corresponds to some block Gaussian elimination. And yeah. Okay, let me just skip some things because it seems that we don't have much time. So maybe to give some intuition for where we're getting, or like how you dynamicize this Schur complement, let's look at this following construction. So let's say we're trying to maintain a Schur complement onto this green subset C, right? The way we're going to think about this is we're going to take every edge outside the Schur complement and we're going to somehow move it onto the Schur complement. And the way you move it is from both endpoints, you run a random walk until you hit the subset C. And you add some edge based on how the random walk looks when you get there. So if you have this red edge on the left, and I want to move it onto C, to the purple edge, I'm going to random walk from both endpoints, and it becomes that purple edge. You can prove that if you sample the random walks and you kind of move every red edge that way, then with high probability that the Schur complement onto C is a spectral sparsifier of what it truly should be. Okay, so now let's say we want to dynamically maintain the Schur complement. So some edge changes, okay? So now let's say that like somehow we need to worry about adding the vertex V to the Schur complement because something around V is changing. Well, because we maintain the Schur complement via random walks, you can shortcut it, kind of just like stop the random walk and change that edge to this edge. And because of the properties we had, this is still a Schur complement. And that's how you dynamically maintain a Schur complement. To actually get the full data structure working, you need a bunch more things, but I'm not going to really go over them. Basically, you have to do this data structure on top of an L2 heavy hitter and then maintain everything. Yeah, I'm just not going to have time to get into it. So let's kind of just keep going a bit. Yeah, sorry. I think starting, okay, cool. Okay, great. Okay, so yeah, let me now give a now let me give a maybe more full algorithmic picture and try to give an analysis or like a heuristic analysis of why this could possibly work. So we're gonna set this factor k to be m to the 1 over 328, and our goal is like something slightly super constant, and our goal is going to be to reduce the amount of residual flow by a factor of 1 minus k over square root m in O of m amortized time. If you can do this, then you're getting slightly better than a total of m to the 1.5 runtime. So the first step is to initialize the data structures, which we're going to call a checker and a locator. Let's not worry too much about the differences for now. So we're going to do it in root m over k phases. In every phase, we're going to split the phase into poly k, I think k to the 4th, batched steps, each of size 1 over k cubed root m. The reason for this is that in the interior point method, we need to make sure we're only ever adding an ST flow. So we need to split it a bunch to get closer to the gradient flow of the central path. Okay. Then we're going to detect for each of these smaller batched flows, what are all edges that are changing by a lot, an epsilon fraction in the ST electric flow. And then we're going to update the resistances of the edges in S that we locate. Okay. So we're going to pass it. So yeah, once you've located these edges, you can or like once you've updated these edges, you pass it back to the data structure, and then you just kind of repeat this loop. And then finally, at the end of every batched step, we're going to pay a nearly linear time to recenter to the exact central path. This is a property of interior point methods. If at any point I'm kind of close to the central path, I can just pay a linear runtime to get exactly back on the central path. So we'll just do that at the end. Okay. To heuristically understand what the runtime is, what you can show is that during this method, that the number of edges with large resistance ends up being some polynomial in k per step. So let's say k to the 16. And let's say the amortized per call of any of these things is m to the 1 minus c, based on the data structures we built earlier. Okay. So compiling all of this, in the first phase, well, like in the first runtime cost, you have to pay m time for m to the 1/2 over k iterations. So this is a m to the 3/2 over k runtime. And in the second part, there's k to the 16th total updates per phase, and then root m over k phases. And then you're paying an amortized m to the 1 minus c per update. So you get something like m to the 3/2 minus c times poly k in the total update time that way for the data structures. If you trade these terms off, you can set k to be something like, well, you can set k to be between them, and then you'll get a m to the 3/2 minus c over 16 runtime, which is less than m to the 3/2, as long as c is anything less than, c is anything positive. So yeah, kind of this sort of trade-off is how we're getting our very crude improvement. Okay. And yeah, in general, this is actually still a simplification. There's a bunch of other IPM stability batching that has to be done, but yeah, that's where our runtime comes from. Okay. So yeah, let me just wrap it up at this point. So to conclude, we gave an algorithm that solves Maxflow in m to the 3/2 minus 1 over 328 log u time. This is the first improvement to the m to the 3/2 runtime of Goldberg-Rao from 98. And at a high level, the way we do this is we think of implementing a sequence of root m electric flow augmentations in amortized sublinear time per iteration. And the data structure that has to be built is detecting the heavy edges in an ST electric flow on a graph with dynamically changing resistances. And yeah, the further, well, okay, let me think how I want to put this. As you might expect, given our runtime, we believe that every part of our algorithm can probably be improved. So one thing is the outer IPM method. I think it would be interesting to design an IPM or to build a better theory of IPMs where this demand that you're solving isn't changing that much, is like kind of a fixed demand. Because it seems like that's like a natural thing you might want, but it seems that all the IPMs don't satisfy that. Additionally, we're losing a ton from the actual data structure that I didn't have that much time to get into. But in general, can you improve the dependencies for the data structures for 1 plus epsilon dynamic effective resistances? And finally, our algorithm had to do some additional work to deal with oblivious versus adaptive adversaries. And I'm curious whether there's a more general theory for making data structures work against adaptive adversaries instead of oblivious. And yeah, okay. And that's all I had.